something which is somehow it is not so difficult. That is, we study what we call the coordinate of a vector relative to a given basis. Suppose that we are consider a vector space V, and V is given with a basis B of V1, V2, Vn. Then we know already that any vector x of V can be written uniquely like x equals C1 V1 plus C2 V2 plus Cn Vn. And those scalar C1, C2, Cn will become the coordinate of x relative to the basis B. And it is written like that, and the coordinate always put in the column. We call it the coordinate matrix or coordinate column of x relative to the basis B. And in order to specify that is the coordinate in the basis B, we put B here, the subscription B, saying that is the coordinate of x in the basis B. And here is some example, very easy one. Given a vector x inside 3 space R3, then its coordinate in the basis, standard basis S will be that one. And you know that a vector space always have more than one basis. So in case it have in case we are given two different bases B and B prime, how we can change the coordinate from one basis to another basis? It is defined in this line. Suppose that V has two bases B of U1, U2 up to UN, and B prime of U1 prime, U2 prime, UN prime. Then if we like in the previous slide, we denote it by V of B, V of B. That is the coordinate matrix of V relative to the basis B, and V B prime is the coordinate matrix of V relative to the basis B prime. Then those coordinate columns will be related to each other by that formula. V sub B equal P multiplied by V sub B prime. So what is the P? P is a square matrix defined as follows. And it is called the transition matrix from B prime to B, ma trận chuyển cơ sở từ B phẩy sang B. And it is defined by the following way. You take U1 prime, and we write the coordinate column of U1 prime relative to the basis B. The second column will be the coordinate column of U2 prime relative to the basis B. And we continue that this way up to the coordinate column of UN prime relative to the basis B. So because that we get P is a square matrix, and we call it transition matrix from B prime to B. And because B and B prime have similar role in that, it means that whenever we change from the basis B prime to B, we can do similar thing to change from the basis B into B prime. That is claimed in the following way. Suppose that P is a transition matrix from a basis B prime to a basis B in I. Then the first claim says that P is invertible. The second claim says that the transition matrix now from B to B prime is P inverse, the inverse of the P of the P. And I summarize it in the following. Suppose that B like that and B prime like that one. Then V sub B equal P multiplied by V sub B prime. And V sub B prime equal P inverse multiplied by V sub B. So what is the P and what is the P inverse? P is defined like that one. You take the coordinate column of U1 prime, U2 prime, UN prime relative to the basis B. And P inverse, we don't have to find the inverse of P. We can do it very easy by this way. You take the coordinate column of U1, U2, UN relative to the basis B prime. So that is the relation between B and B prime and how we can change from the basis B into B prime or vice versa. And the way to find the transition matrix from B to B prime or from B prime to B, that is quite similar to the way we apply Gauss-Jordan elimination to find the inverse of a matrix. Here it is claimed as follows. Let B and B prime like that. If you want to find the transition matrix from B to B prime, as in previous slide we denoted by P inverse, it can be done as follows. You put B prime and B side by side like that, you get n by 2n matrix. Then you apply Gauss-Jordan elimination to change the first part into the identity matrix. Then the second part will become something, and that something is exactly the transition matrix from B to B prime, and it is a P inverse. And after that, we begin with the lecture on inner product space. We begin from the model which is very familiar to us, that is n space Rn. In Rn, we can define the dot product and the length. The length is defined as follows. If V has coordinate V1 up to Vn, then the length of V will be defined by square root of V1 square plus V2 square plus Vn square. The length sometimes can be called the norm. In the general case, that is the case of inner product space. Usually it will be called the norm, but here we can call it the length. For the length, we have here on the screen, I list 4 properties, but however, the property number 2 is not a property, it is only the name. A vector has length 1 will be called a unit vector. And we consider the case when U equal C times of V. And suppose that both U and V are non-zero vector, then C can be one of the following cases. One of the following cases. C can be positive or negative. If C is positive, we say U and V has the same direction. If C is negative, we say U and V have opposite direction. And in case V is non-zero and not yet unit vector, we can divide V by its length. We get the unit vector and we call it the unit vector in the direction of V. That is here. Divide by the length, we get the unit vector in the direction of V. And the process of finding unit vector in the direction of V, we has named normalizing the vector V. That is the main ingredient of the class today. Then after that, we define the distance between two vectors U and V. Suppose that we are given two vectors U and V. Then the distance between U and V is defined to be the length of the difference U minus V. And the distance have 3 properties in here. I describe it here for you. Next, we define the dot product in Rn. The dot product is defined by U1 V1 plus U2 V2 plus UN Vn. If U equal that and V equal that. And if you remember, in Vietnam, I believe that you know that already. If you consider the n equal 2 or 3, that is what in high school you call it tích vô hướng. That is same by the same formula like that. And here we call it the dot product. And this observation or this theorem give you the property of the dot product. I list 5 property here, but however, property number 4, v dot v equals square of the length of v. You can forget it because that came from the definition. However, we have 4 important property: 1, 2, 3, and here is a property number 4. I consider it. Please keep in mind that we need 4 property of the dot product because we are going to borrow those property to define something else later. Now, that is the notion of Euclidean n space. The vector space Rn together with a vector length and the dot product will be called Euclidean n space. Không gian Euclid n chiều. Now for that Euclidean n space, we have the Cauchy-Schwarz inequality, saying that absolute value of u dot v is less than or equal the product of the length of u and the length of v. And after that, we define the angle between the two vectors u and v. That is an angle zeta satisfying the cosine of zeta equals the dot product of uv divided by the product of the length u and the length of v. And here we suppose that the value of zeta lies between 0 and pi. And with that, we have 5 cases as here. The first case is that is, we say the flat angle, góc bẹt, or we say that is a case when two vectors show the opposite direction. The next one is here. That is the case of obtuse angle, góc tù. And in the middle, we have the case of the right angle, góc vuông. And here is the acute angle. And the last one is the zero angle. Two vectors have the same direction. You should note that we cannot define the angle between zero vector and another vector. But however, we can, you see here, the zero vector is considered to be orthogonal to any other vector. That is something very funny. First, I say that the two vectors u and v will be orthogonal if the dot product equals 0. And because of that, we can consider the vector 0 is orthogonal to any other vector. If we look at the geometry meaning of orthogonal, it has no meaning. Consider that 0 is orthogonal to any other vector. We have one more inequality, has a name triangle inequality. Suppose that you are given two vectors u and v in Rn. Then the length of u plus v is always less than or equal the length of u plus the length of v. And the next one I will tell you that is a Pythagorean theorem. U and v will be orthogonal if and only if square of the length of u plus v equal square of the length of u plus square of the length of v. This slide will show you the dot product and the matrix multiplication as the same. Why that? Because usually the coordinate columns of a vector is written like that, and the dot product is given by that one. But if we take U and take transpose, you get the rows matrix like that. And because of that, you can multiply them with the coordinate matrix like that one. And then if you look at the formula, it is nothing but the dot product. So it is written in the red frame like that. That is U dot V equals U transpose multiplied by V. Now I go into the notion of inner product space. We borrow four property of the dot product to define what is the inner product. Suppose that V is a vector space. Then on V, an inner product is a function satisfying four axiom like that. And a function is some rule, some correspondence to send any pair, a pair of two vectors U and V into a number denoted by UV between the sharp bracket like that. And that function need to satisfy four property here. And those property are absolutely the same property of the dot product I claimed in the previous slide, serial previous slide. And vector space V together with an inner product will become an inner product space. So inner product space is a vector space together with an inner product. And here is some example. The first example is obviously that is n space Rn. Why is that? Because we borrow the property of the dot product to define the inner product. So obviously that one is inner product space. But however, example 2 show you that on the same vector space, you can have different inner product space. You can have usual inner product like here. But here in the example, I give you another inner product defined by that formula. That is not the usual dot product, but it is still an inner product for R2. And I claim that in Rn, any inner product must be of this form, which on Ci must be positive number. And along the lecture class, I gave you already the case of a function of this form, but one of the coefficient Ci is a negative, then at least one of the four axioms is broken, is not satisfied, and because of that, the formula does not give an inner product. And here is some property of inner product I show you here. And today we begin the class from this point. Here is it. Now let me continue. Now the class will begin from here. The lecture will begin here. We have the property of inner product is something like that. The inner product of zero vector and with any other vector is always zero. And for the inner product, we have that. That is a property of distributivity. And that one is some kind of, how to say, some kind of associativity. And also, similar to similar to the dot product or similar to the Euclidean space, we can define the norm of a vector U in an inner product space. We can define the norm by square root of inner product U and U. And the axiom number 4 in the definition of the inner product allow you to put the inner product of U and U under the square root here. That is never negative, so we can put it here. And by that, you see that square of the norm equals the product of the inner product of U and U, like that. And also we can define the distance between U and V. That is the norm of the difference U minus V. Or by formula, you take the square root of that inner product. So that is quite similar to the Euclidean n space. Also, the angle between two non-zero vectors U and V can be defined by zeta, satisfying that the cosine of zeta to be that one. Here is inner product and divide by two things. That is the angle between the two non-zero vectors. Next, we define the notion of orthogonal. Whenever we define the angle, we can define the notion of orthogonal. Now, two vectors are orthogonal if and only if the inner product of U and V equal 0. So, I'm sorry. Please remember that two vectors can be orthogonal according to one inner product, but it can be non-orthogonal if we consider another inner product. You see, on the same vector space, you can define different inner product. So maybe with this inner product, the two vectors are orthogonal. But if for another inner product, they will not be orthogonal to each other. So you should be careful with that. Now, we consider the case when V equal has norm 1. Then we call it a unit vector. But in case V is not yet unit vector and V is non-zero, then we can define, we can normalize it to get the unit vector in the same direction. Divide by the length, we get the unit vector in the direction of the vector V. Here is some example for you. We consider P like that and Q like that. They are two vectors in the vector space of on polynomial with degree less than or equal 1, equal n. Then, if we define the inner product of P and Q to be that one, that will make P and X become an inner product space. Now, if you consider P and Q like that in the space P2X, that is the space of on polynomial of degree less than or equal to, then you are required to find what is the product of the inner product of P and Q, what is the norm of Q, and what is the distance between P and Q. Then just only some very simple calculation. The first one, P multiplied by Q, I mean the inner product of P and Q. We use that formula and you get the inner product of sums equal to, and the length of the norm of Q equals square root of inner product of Q and Q. And because Q to be that, then the norm of Q equals square root of 21. Finally, first you need to find what is a P minus Q. P is here, Q here. P minus Q to be that one. So the distance between P and Q equals the length of P minus Q, and to be that. And finally, you get it is a square root of 22. So that is A, B, and C here. Now, next I explain to you. We have a three property of norm. The first one saying that the norm is never negative, and it is equals 0 if and only if U is a zero vector. And if you consider the norm of C time of U, it equals absolute value C time of the norm of U. That is very easy to imagine. And also we have a property of distance. Again, the distance is never negative, and the distance equals 0 if and only if two vectors coincide each other U and V. And the last one, the distance between U and V and the distance between V and U are the same. And also we have three things as in the Euclidean n-space. The first one is a Cauchy-Schwarz inequality here. The second one is a triangle inequality, absolutely similar to that for the dot product in the Euclidean n-space. And the last one is a Pythagorean theorem, saying U and V are orthogonal if and only if we have this equality. So that is nothing changed if we take the slide on the dot product in the Euclidean space. Now I am going to tell you the notion of orthogonal projection in the inner product space. Here, suppose that you are given two vectors U and V in an inner product space V. And I suppose that V, the second vector here, V is non-zero. Then we can define what you call orthogonal projection of U onto V. That is a vector projection must be a vector in V, and it is given by a formula that or if you look at the formula only, it is not so easy for you to imagine. But however, you can see it here. If you look at the picture like that, U will be that vector and V will be something here. Then the orthogonal projection of U onto V is that one. That one. Or you can consider it is a vector going from the origin to that point. And it will be a multiple time of V because V is here. And that lying on the straight line containing V. So it is a multiple time of V. So multiple time is that number. That is the meaning of the formula. And I summarize. In the case, we accept the formula like that, but I consider the special case when V is unit vector already. And because V is unit, the inner product of V and V equals square of the length of V and equal 1. Then the formula will became that one. Orthogonal projection of U on V equals inner product of U V multiplied by V. So now it's much simpler formula. And here is some example. Suppose that you are given C space RC with the standard inner product, I mean it's a dot product. Now you need to find the orthogonal projection of U on V. How you can do it? You apply the formula I give you in the previous slide. You have inner product of U and V equal 10 and inner product of V and V equal 5. So the projection of U on V equal that, and it is by computation you get 2, 4, 0. And you see 2, 4, 0 is 2 times of V. 2 times of V. And there is one important observation. That is, if you take U minus projection of U on V, it will be orthogonal to V. We are going back to this point later. And that is a property of orthogonal projection. That is a property about the distance. I give you the claim first, and then I explain that by geometry. Suppose that you are given two vectors U and V, two vectors inside the inner product V. And suppose that V is non-zero. And because of that, we can always define the orthogonal projection of U and V. In that case, the distance between U and its orthogonal projection on V is always less than the distance between U and any vector of the form multiple times of V. And here I have one condition, that is C is different from that number. I explain that to you by a picture. Please take a look at this. U to be that one and V to be that one. Now we consider the projection of U on V. By point, it is here, or by vector, that is a vector going from the origin to that one. Next, if I consider a multiple time of V by CV, that is somewhere here, must lie on the green line here. Any vector lying on that. And I require that C is different from that number, so that C of V cannot be that point. That point and that point cannot coincide each other. Next, I see that. Then the inequality saying that the distance from U to projection is always less than the distance from U to any other point of the form C of V. So that is what I mean by this inequality. Or in Vietnam, if you want to say, đường cao bao giờ cũng ngắn hơn một cái đường bất kỳ như thế này. Khi mà bạn hạ vuông góc xuống thì bao giờ cái khoảng cách đấy cũng là khoảng cách ngắn nhất. So that is the meaning of the inequality like that. Next, we study what we call the autonomic basis and most complicated formula of the whole course on linear algebra. That is the Gram-Schmidt process. Anyway, we begin right now. I am going to give you a definition of what we call orthogonal set. A set S of vector in an inner product space V will be called orthogonal set if I take any pair of vector in the set S, they are always orthogonal to each other. Here by formula, if S equals V1, V2, Vn, then Vi, the inner product of Vi and Vj, is always 0 if I is different from J. Then S will be called an orthogonal set, một hệ trực giao. But if more than that, we can define the autonomous set or autonomous system. It is as follows. An orthogonal set already, but now in which any vector is a vector, is a unit vector, then we will call the autonomic basis, and it is here. We require that the inner product of Vi and Vj equals 0 if I is different from J. That is like here. But we require more. That is the inner product of Vi and Vi equal 1. Means that the Vi has a length, has a norm 1. Then we call it an autonomous system, autonomous set, một hệ trực chuẩn. You have the word normal means chuẩn. The last one of this slide. In case S is a basis, if at the same time S is an orthogonal system, then S will be called an orthogonal basis. And if S is an autonomous system at the same time, then S will be called autonomous basis. Nếu cơ sở S đồng thời lại là một hệ trực giao thì chúng ta gọi là cơ sở trực giao. Nếu đồng thời nó là một cơ sở trực chuẩn thì ta sẽ gọi nó là một nếu đồng thời nó là một hệ trực chuẩn thì ta sẽ gọi nó là một cơ sở trực chuẩn. Autonomous là trực chuẩn, orthogonal là trực giao. And here is some examples for you. Quite easy for you to imagine. In the high school, we know already if you take the coordinate plane like that, and if you take the unit vector I and J with the coordinate like that, then I and J will make a basis for two space R2. And more than that, I and J are orthogonal to each other, and both of them has a length 1. So that one is an autonomous basis for the plane. Similarly, for the case of space, I mean the R3. Here. We have a 3 vector makes a standard basis for R3, as I show on the screen. And obviously, it is very easy for you to verify that those vectors are orthogonal to each other, and each of them has a norm 1. So that one is again an autonomous basis for R3. But that one show you again in R3 we have another autonomous basis that is no longer standard basis. Now we consider S to be that one, V1, V2, V3. Then we can verify that the dot product of V1, V2 equals 0, of V1, V3 equals 0, and V2, V3 equals 0. So that is they are V1, V2, V3 are orthogonal to each other. Now we verify the length or the norm of each vector. The norm of V1 equal 1, of V2 equal 1, and of VC again equal 1. So S is an autonomous set, and because we know already that S is a basis, so we get an autonomous basis. But once again, I would like to remind you that is no longer standard basis. That is a new one. That is another example, but I think that we should stop here for a short break, and we're coming back after 5 minutes. So please take a break.
Mấy chị cái sạc iPad tí.
Can you continue now?
Yes.
Oh god, she's
Yes.
one of those YouTubers that
Okay.
like all the comments so that you can't tell what people actually think. It's really good. YouTube removed the dislikes and now they have this. There's nothing left.
So
She likes all the
before the
good
break,
ones, so they show up, right? Whatever, I don't
we
care.
consider
This is so gross.
the case
I love seafood, but this is
non-standard
nasty, dude.
autonomous
Stop it.
basis for
I don't know what
R3.
it is with like young Asian girls
And we continue
eating
with the
really nasty
examples
food.
now.
Why?
We consider the case of autonomous basis for
Stop it! We're not watching
P3
that.
of
I've
X.
decided. You're welcome. Then of
Once again, I repeat that P3 means the vector space with the vector space of all polynomial of degree less than or equal 3. Now, if we define the inner product to be like that, for P equal that and Q equal that, then the example number 2 require you to show that the basis B of 1x and x2 is an autonomous. Oh, sorry, I make a mistake here. Here, that one.
Of course, there's this. This happened in
Is it
2019
two,
after
not
I
three?
made my video, and it's
No,
it's just wild.
I am
Octopus
considering
attacks a live
the
streamer
space
as
of
she tried to eat it
P
alive in
2
China.
of x, that is space of all polynomial of degree less than or equal to, not 3.
Jesus Christ!
I'm sorry
this feels
for
like
that.
straight out of Nightmare. This is the stuff that shows up in my dreams, and
Then
I
the standard
wake up and
basis
you're like, oh,
B consists
God,
of
thank God that didn't
1x
happen.
and x
I never thought I'd
squared.
actually root for the.
It must be an
for the
autonomous. That is
octopus.
the
This octopus
requirement of
accomplished
the
something great in his life.
example.
It would be an
How you can do it? Here I write V1 to be that, V2 to be that one, and V3 to be that one. Then we consider the inner product of them to be that. On the inner product are 0. So we know that the system V1, V2, V3 are orthogonal system. The next, we consider the length or the norm of each vector V1, V2, V3.
Up in my dreams,
Then
and I
you
go,
get that the system V1, V2, Vc is an autonomous basis for P2x. And you can consider that the homework number 2, I put it here. That is, if you consider the space Pnx of all polynomial of degree less than or equal n, then the standard basis 1x, x2, xn minus 1, xn is an autonomous basis. You can do by the same way like that, just only to replace the number 2 by n. Yeah. The next one, that is a very interesting property of orthogonal set. Suppose that S is an orthogonal set of vectors inside inner product space V. But more than that, I suppose that all vector inside S are non-zero. None of the Vi is a zero vector. Then S must be linearly independent. In phrasing, I can say an orthogonal set of non-zero vector is always linearly independent. Is always linearly independent. It's explained here. I will not repeat it here. You can read it on the Moodle by yourself. But however, we can use that. We can use that property to verify some things to be a basis or not. I repeat to you that sometimes in your exercise, you need to prove something to be a basis, or you need to find find basis for some subspace or something like that, then you remember that you need to do two things. The first one, you need to show that the set is a spanning set. The second one is a linearly independent. But however, you can use the property in the previous slide to show something to be a basis as follows. Suppose that V is an inner product space, and also we know already that the dimension of V is n. Then any orthogonal set of n non-zero vector is always a basis for V. Why is that? Because the set of the orthogonal set of non-zero vector is always linearly independent, and because the number of vector is n, is exactly the dimension of the vector space, so it is a basis. We know that already. And here is some example for you. Suppose that we consider 4 vector v1, v2, v3, v4 inside 4 space R4. That we know already has the dimension 4. And we consider v1, v2, v3, v4. Obviously, they are non-zero vectors. And they are, if we consider the inner product or the dot product, they all are 0. And here also. So the system is orthogonal. And because non-zero and orthogonal, so they are linearly independent. And because they are linearly independent and the number of the vector is exactly the dimension of the space, so it is a basis for R4. Now I explain to you one advantage of the autonomous basis. Why we need to define an autonomous basis? You know that given a basis for a vector space, we know any vector can be given by the coordinate column of a coordinate matrix. But in case the basis is an autonomous basis, it's much easier for you to find the coordinate matrix here. Suppose that B is an autonomous basis for inner product space V. Then if you are given a W is any vector inside here, then the coordinate column of W relative to the basis B is given by the following formula here. V is written in the form of a linear combination of V1, V2, Vn, and on the coefficient win B like that. It is explained here. I will not stop at the explanation. I don't like it, but I want to explain to you by looking at the other way. Here, B denoted an autonomous basis for V, and W is any vector inside here. Then the corresponding coordinate matrix of W is given by this form. The coordinate column or coordinate matrix relative to the basis B, win B here. The first coordinate will be the inner product of W and V1. The second will be inner product of W and V2, and so on. And the last one will be the inner product of W and Vn. So we have that. That is advantage of an autonomous basis. Very easy to find the coordinate of any vector. And here is some examples. We consider a vector W like that in R3. And suppose that in R3, we are given an autonomous basis like that. That is not the standard basis. That is something strange, the non-standard basis. But we know already the basis is an autonomous basis. Then, if you are required to find the coordinate of W relative to B is very easy. The first coordinate will be inner product of W and V1, and you get that. The second coordinate will be the inner product of W and V2, and you get that one. And finally, the last coordinate will be inner product of W and V3, and you get 2. So the coordinate will be -1, -7, and 2. The next slide, I show you once again the orthogonal projection in inner product. Before the break, we consider already the orthogonal projection of one vector on another vector. Here, I repeat it here. Suppose that we are given U and V, two vectors in V, and V is non-zero. Then the orthogonal projection of U onto V is given by that. And it is here by picture, you can see it here. And we have one important property, that is U minus projection of U is always orthogonal to the vector V. Now I am going to define what we call the orthogonal projection of a vector V on a subspace. Suppose that W is a subspace of V, and V is any vector inside the space V. Then the orthogonal projection of V onto the subspace W, that is a vector in W denoted by projection of V on W, so that the V minus projection of V on W is orthogonal to W. So I borrow that property to define the orthogonal projection of V on the subspace W. Here, once again, I put it in the red frame to see that we use that in defining the orthogonal projection of V on W. And you can take a look at that thing. The picture is here. W is a plane like that, and V is outside, is a vector outside. Then the orthogonal projection of V will be here, and you see the V minus projection of V on W is exactly the red vector here, the red and dash vector here. And obviously, that vector is orthogonal to the plane or to the subspace W here. That is a definition of orthogonal projection on the subspace. Now, I came to the most complicated formula or complicated procedure in the course. It has named Gram-Schmidt autonomalization process, trực chuẩn hóa or trực giao hóa Gram-Schmidt. So what does it mean? Suppose that we are given, I'm sorry, somebody asked some question or something. Suppose that we are considering an inner product space V, and in that we have a basis, any basis B of U1, U2 up to UN. Then Gram-Schmidt process will help you. From B, we can make an autonomous basis, a new autonomic basis for V. It can be done as follows. The first step, we take V1 to be U1. It means nothing changed with U1. We keep it. Second step, we make W1, that is subspace of V spanned by V1, That is the first step. The first step, you can consider both things here. Second step, you take V2. V2 is U2 minus projection of U2 on W1. Or by formula you get, it is here. And if you remember here, V minus projection of V on W is always orthogonal to W. So because of that, please remember the formula. Please remember that formula in the red frame. Then here, then obviously V2 will be orthogonal to W1, and W1 is spanned by V1. It means that V2 orthogonal to V1. Then now I make W2 to be the subspace of V spanned by V1 and V2, because here we have V1 and V2 already. Then the third step, I take V3 equals UC minus projection of UC onto subspace W2. Or by formula, you get that one. And obviously, by the observation in the previous slide, in the red frame, that is, that vector is always orthogonal to W2. It means that V3 is orthogonal to V1 and V2. So we can continue it this way up to the last one. The last one is Vn equal Un minus its orthogonal projection on Wn minus 1. Or by formula, you get that thing. By this construction, you get a system V1, V2, V3, up to Vn. And that is already an orthogonal basis. That is already is an orthogonal basis. And the rest is we normalize it by dividing each vector by its the length, like that one. You get an autonomous basis. So you see from B, first we get B prime, that is an orthogonal basis, and finally you get B double prime. It is already an autonomous basis. On the process going from B to B double prime has named Gram-Schmidt autonomalization process. So that is what we call Gram-Schmidt. And because of the formula here, I tell you that is the most complicated formula in the course, because it requires you to remember that one. And by the example here, we show you the easiest case. Now we consider the case when V is a coordinate plane, and we consider the basis B consists of two vectors V1 and V2. V1 is here and V2 is here. That is in gray color. B consists of V1 and V2. It is not yet an autonomous basis, and even it is not yet an orthogonal, and we need to apply the Gram-Schmidt to find an autonomous basis for R2. How we can do it? We follow the process in the previous slide. The first step, we take W1 equal V1. W1 and V1. Then the second step, we choose W2 equal V2 minus projection of V2 on V1. Projection of V2 on V1 is that vector. And V2 minus projection of V2 on V1 means the vector going from that point to this point. Or if we put that vector at the origin, you get W2 to be that one. So now we have W1 is here, W2 is here. It's already orthogonal. It's already orthogonal to each other, but not yet normal, not yet the unit vector. So the last step, we normalize it by dividing by the length. You get an autonomic basis of A2. So that is some example to show you what the Gram-Schmidt process is. That example is by geometry. Now I give you another example by formula. You consider B consists of U1, U2, and U3 as on the screen. You need to apply the Gram-Schmidt to find an autonomous basis for A3. Now, you choose V1 to be that, you keep it. V2 to be that one, and you get it. Just only apply the formula I gave you already. Then V3 to be that one. So finally, you get V1, V2, V3 to be that one, and that one. And yeah, you see, B prime consists of V1, V2, V3 is already orthogonal basis, but now we need to I'm sorry. We need to normalize it to get the autonomous basis. Here, we divide any vector by its length. You get that one. So that one is already an autonomous basis for A3. Another example for you. That is sometimes you are required to find an autonomous basis for some concrete subspace. And here in this example, you are given a system of linear equation. First, you need to find the solution space, and then you need to find an autonomous basis for solution space. Then, how you can do it? The first step, you apply Gauss-Jordan elimination to find the solution space. It is here. The first and second column containing the leading one. So the second, the third and the fourth is a free column. Means x3 and x4 are free variable. By free variable, we can give it any value s and t. And then you can find x2 to be that and x1 to be that one. And because of that, you get the solution space will have that form for any number s and any number t. That is, the basis for the solution space is that vector and that vector. The two vectors here are basis for a solution space. But it is not yet autonomous basis, so we need to apply the Gram-Schmidt to find an autonomous basis for solution space. And it is here because we have only two vectors, so it is very easy to do the calculation here. You get V1 and V2 is orthogonal basis like that. Now we normalize it, you get that one. B double prime with that. That is already the autonomic basis for solution space. Next, we consider what we call mass modulus and least square analysis. That is the last section of the lecture number 5, and that is a kind of application of linear algebra. First, we define what we call the orthogonal subspace. Here, suppose that we are given two subspace W1 and W2 of an inner product space V, and we say that W1 and W2 are orthogonal to each other if and only if you choose take any W1 and any V1 and any V2 inside W1 and W2, we always have the inner product of V1 and V2 equal 0. Then in that case, we say W1 and W2 are orthogonal to each other. It is very easy for you to find the example from the geometry in the high school, so I leave it for you to imagine by yourself. Here is some example. Once again, I put it like a homework. You please do it. Suppose that we have take two space W1 and W2. They are subspace of R3, of C space R3. The first space is generated by two vectors like that, and the last one, the W2, is spanned by only one vector like that. Then please verify that W1 and W2 are orthogonal to each other, and it is explained here already. Next, I define what we call the orthogonal complement of W. Suppose that W be any subspace of an inner product space V. Now, a vector U in V will be said orthogonal to W if U is orthogonal to any vector inside W. That is the first one. If you consider the set of all vector in V which are orthogonal to any vector inside W, then we get what we call orthogonal complement of W. That is the name we need to define it. Orthogonal complement of W in Vietnamese, phần bù trực giao of W. Or by formula you have W perpendicular equal the set of all V inside here, so that the inner product of V and W equal 0 for all W inside the subspace W. Okay. And we have the remark, because we know that for any vector space V, we always have trivial subspace 0 vector space and the whole V. Then if we take the orthogonal complement of 0 vector, you get V. And if you take the orthogonal complement of the whole vector space V, you get 0 vector space. So that is a trivial cases. Now suppose that W is a subspace, any subspace of V. Then we have the following property. The first one, the orthogonal complement of W is always a subspace of V. The second, that is the intersection of W and W perpendicular is always 0. It means that W and its orthogonal complement intersect at only one point. At only one point. One point is origin, that is a 0 vector. And if you take orthogonal complement 2 times, you will go back to the subspace W. Okay. And here is some example for you. The example is explained here. If you consider V to be the coordinate plane A2 and the subspace W equals OX, that is X axis, then the first one, the W perpendicular now will be the Y axis here. It is obviously a subspace of A2. And if you take the intersection of W and W perpendicular, and that line intersect at only one point, that is origin, and is 0, 0. And if you take one time of orthogonal complement, you get that thing. But if you take once again the orthogonal complement of that, you once again you get the X axis. So that example will show you what is described in the claim here. And the question for you here. Now, if you consider V to be the 3 space like that, and we consider again, we consider W to be the X axis like that one. So then what is the W perpendicular? Bạn nào làm ơn tắt hộ cái mic đi ạ.
Bắt tờ. Không hiểu cái gì đấy.
Okay, let me continue. Now, my question is, in case you consider the space V to be the A3 and W, the subspace W is still X axis, then what is it? W perpendicular. You can consider it as a homework. Let me continue. Yeah. The next will be the notion of direct sum. Suppose that we are given two subspaces of Rn, say W1 and W2. If each vector x of Rn can be written uniquely as a sum of a vector W1 inside here and W2 inside here, that is, we can write x equal W1 and W plus W2 like that, but in only one way, uniquely like that, then Rn, the space Rn, will be called the direct sum of W1 and W2. And in that case, we write like that, n equal 1, n equal W1 plus direct sum of W2. And for that operation, usually American people say O plus, that is something in the middle, and O, that is something around the circle around the plus sign here. Yeah, here are some property for orthogonal subspace. The first one say no. For W is any subspace of Rn, then we have the following property. The first one, we have the dimension of W plus dimension of W perpendicular equal n. The second is Rn is always direct sum of W and its orthogonal complement. And that we say already. If we take Debon's orthogonal complement, you get back to the subspace itself. So that is the property of orthogonal subspace. The next slide show you the formula for you to find the orthogonal projection of a vector on a subspace. The definition we know already. We know already how we can define the orthogonal projection of any vector on a subspace. But now, in case the subspace is given together with an autonomic basis, it is very easy to write down the vector in the formula. It is here. Suppose that W is a subspace, and inside the W we have an autonomic basis, say U1, U2 up to UT. And V is any vector inside the vector space V. Then the projection of V onto the subspace W will be given by that formula. And it is explained here, so I will not explain once again during the class. You need to read it by yourself. Here is some example for you to see. Now, suppose that you are given W1 and W2 like that, and V is a vector with the coordinate like that one. You need to find the projection of vector V on the subspace W spanned by W1 and W2. How you can do it? How you can do it? The first one, you see that W1 and W2 is already orthogonal basis. They orthogonal to each other. But however, it is not yet autonomous. So we need normalize it. Normalize it by divide each vector by its length. So that one is already an autonomous basis for W. Then with that, we can apply the formula in the previous slide. You get then the projection of V on W equals that one. Then you need only to find the inner product here, inner product here, and you multiply by U1 here and U2. And finally, you get that thing. That one is orthogonal projection of V on the subspace W. Once again, the orthogonal projection has a very interesting property concerning the notion of the distance. It is here. I write it and then I will show you by the picture. Suppose that W be any subspace of an inner product space V, and V is any vector inside here. Now, if you consider any vector W of the subspace, and suppose that W is different from the project of V on W, then the distance from V to its orthogonal projection is always less than the distance from V to W. Or in other words, you can say the V minus the length or the norm of V minus projection of V on W is minimum of the norm of V minus W, with all vector W lying inside the subspace W. Now that is by formula. But however, you can see it by geometry as follows. Here, you take W to be the subspace like that, and V is a vector outside somewhere, and it has orthogonal projection is here. I write it like a projection of V on W. Now we consider any omega or any W on the same subspace but different from the projection. Then with that, obviously the distance from V to that point is always less than the distance from V to that point. That is the meaning of inequality I write in the previous slide. In the previous here. That is an inequality, and it is explained here. The length of the vector here, or the norm of the vector here, is always less than the norm of that vector. That is very easy for us if we see the picture. And here are some explanation by using the Pythagorean theorem. So you need to read it by yourself. And then I have two remarks here. The same inequality, but however, you can explain it in wording by two remarks like that. It means that among all scalar multiple of a vector U, the orthogonal projection of V onto U is the one that is the closest to V. And also the same things, if we consider the projection of any vector on a subspace W, that is among all the vector in the subspace W, the projection of V on W is the vector which is the closest vector to V. We are going to use that in next week, not today. I think that we should stop at this point. The next week we use the previous we use those property to do what we call the least square problem. And also before that, we consider the fundamental subspace of any matrix, and in that case we consider they will be orthogonal complement to each other, and we can apply that in doing some application of linear algebra. So that is what we are going to do next week, and today we stop here. I see that in the chat box, some of you asked me some of you asked about the midterm exams. We register with the university for that. We can take our midterm exams on 18 or 19 December, but not yet receive an answer from the IT unit. So we need to be confirmed. But however, please be ready for that date for exams, for the midterm exam. So I see that you have the assignment for the week already. So please do it. And we stop here today. And if you do you have any question for my lecture today?
I have a question.
Please.
For the midterm test, we need to review from the first lecture to this lecture.
I did not understand what is here.
Midterm thì bao gồm những kiến thức chưa nào ạ?
So usually during the tutor class, if you finish any part of the during the tutor class, then you will do until that point, you see. But however, next week I will claim to you that we claim to you at this point we can have our midterm exams next Wednesday. Okay.
Okay. Okay.
Some more thing. Oh, somebody asked me to slow down a little in the next session. No, I don't think so. It is impossible for me because our program is still very long and I am doing very slowly. The most important thing that is you need to read the slide before the class, then it will help you to follow the lecture. Okay, so if no more question, I'd like to say goodbye to you and we'll see next week.
Goodbye, Professor.
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 Thank you, Professor.
Thank you, Professor.
Goodbye, Professor.